Okay. On Monday, we almost covered the single linked list or singly linked list. We saw how to create one. First, you create a node, then you create the chain out of the node. And then we discussed why you may need another class that is called linked list, although in the very first lecture we created a complete list from just the class node, right? Remember this? And then we said this is because if you just identify your list with adding a single variable, which is head, now you have access to the full list, right? So this is the thing that is needed for head. Another reason for having the bigger class, which is the single linked list, is now you can add instance methods to this class. And we have seen inserting a node at the beginning, which is at the front, inserting a node at the middle. You guys should be able also to write a method that insert at the end or at the rear or at the tail. And then we also have seen how to traverse a list, which we discussed also that it should be an instance method of the single linked list class, not the node class, and not a standalone in the main or in a test class, right? These are all reasons why you should have a class that is called single linked list, right? Good. And we stopped here. Before this, we discussed how to delete a node from a single linked list. If you have a certain value and you want to delete the node that has this value, how to do this? How to delete a node from a single linked list? I don't have much to say today, so I'm okay waiting for 5 minutes for someone to volunteer and say how we delete a node for a single linked list. Yep. Yeah, so what are the steps to do this? Like, I gave you a value, an int, assume this is a linked list of integers. Then I say delete the node that has this value. How to do this? What you say is correct, but let's take it a more structured way. Yeah? Yeah, which is very similar, but yeah. You don't want to insert, right? We want to delete, remember this. Okay, so you find the one that you want to delete, good. I find the one after that. How to find the one before that? In a single linked list, you just move forward. You cannot go back. If you are in the node right now that you want to delete, you cannot see what is previous, right? What is your predecessor, or what is the previous one, or what is the one that is pointing into you, right? You only see what you point to. And this is the main trick. What is that? Yes, what you are saying in other clear words is, instead of finding the node that you want to delete, find the one directly before it, right? So instead of looking for the value that is you are currently in right now, always traverse. Now what you said is traversing a list. This is the first thing you need to do because you want to find a certain value, right? And we have seen how to traverse a list. You keep looking from the head until you encounter a null pointer, and you compare the value that is in your current, or what we call here, node, with the value that you want to delete. Is this the value? If it is yes, that means now you are in the node that you want to delete. The problem with this is if you reach to the point that you are in the node that you want to delete right now, how can you delete it? What you said is you want to make the one that is before it point to the one that is after it. But I don't know what is the one that is before me. This information is not available in a single linked list. So instead of doing this, keep traversing with the reference or a pointer or the current node that you are looking for. But instead of checking here.value or current.value, check current.next.value, which means now you will keep moving, walking in each node until you stop at the point where the next node is the one that has the value that you want to delete, right? And then in this case, you are one before it, so you are safe. And then what you can do right now is make this next of this current node, which is before you, point to the one afterwards. right? This is one way. Another simpler way, but you need two references for this, is instead of defining one reference, which you move with to traverse, you define two, right? And then make a one, and this is not in the slide, so maybe you guys should pay attention to this, because this method can be solved with what I just said, but many problems in linked lists cannot be solved using a single pointer or reference. And the trick is to define two. One, for example, is moving faster than the other, right? In this case, you want to make a one. Can someone imagine if I use two references, how to get this, how to delete a node? So we want to write a method that also has a value that I want to delete, and you use two references for this. I mean by two references, like you define, instead of defining a here node that you keep moving forward, you define maybe here and next to here, or here and before here, something like this. How to do that? This is a bonus mark. Yeah. So the new node, you are talking about insertion as well, right? We want to delete, so we don't want a new node. We just want to remove a node. But what you are saying is correct. But let me ask you, how I start? Now I have two references, right? So previously, when we had only one reference that we called here, we started from the head, keep moving, right? If I have two, where both should start? From the head as well? Yeah, this is one way, or the other way is start the one that is before at the head and the one that is current at the head next, right? But what you're saying is correct. Make it as the null and then the one that's currently at the head. Basically, make a one directly before the other, right? Then keep moving both. So if the one that is current at the one that you want to delete right now, which means the one that is before it is at the node that is before, right? And then you can do this. This is a very simple trick of using two references, but put this into account because this trick is very important. You usually use the encoding interviews. Like using two references has a lot of problems that you can look for. Yeah. But then what is the benefit of having a one that is at the end? Yeah. Oh, but this is not a sorted list, right? What you're talking about is the one that is a sorted list, right? Yeah, this may work for a sorted list, but our list is not sorted, which means the value can be anywhere, right? But generally what you're saying is correct. And if you move them with the same speed, they will always meet at the middle, regardless of the value, right? Because one is moving here, one is moving here. Assume you have 8 nodes. You start from 8 and from 0, you will meet at 4, right? Okay. Is there any question? Good. So having this problem with deletion, that you need to identify the node that is before you or use two references or use the trick that I just mentioned, tells you that there is a need that you want also to know the node before you, right? Now we only have a single link, so it's called singly linked list, that points to the next, right? So this introduces what we call doubly linked list. You don't only point to the next, you also point to the previous one, right? So you have a chain now that you can traverse forward and backward, right? Clearly there are advantages here, right? Okay, so in a doubly linked list, each node has the next link, which is the black one is just simply a simple single linked list, but also you have the backward one with the previous link, right? And in this case, for example, if I want to delete this one, what I would do? Simply make this one point to this one point to this, and then it's deleted, right? Now you don't need two references, or you need to know the one that is before you because you already have a link to that, right? Make sense? So for a doubly linked list, given, so let's first start from the single linked list. We said in a single linked list, you have two special nodes, the one at the beginning and one at the end, right? The one at the beginning that we call the head, it doesn't have something before it, which means it's not the next of any node, right? Right? But then the one that is more special is the tail node. Why it's special? Because it doesn't have a next. Then we said, what do we do for the next of the tail? What is the next of the tail node in the single linked list? Very dumb question. Null, right? It's very dumb, but it's very important, because if you don't have this null, and this is partially one of the mistakes that people do when write code, the main problem with this is you don't actually have a list. Because if you want to traverse, you keep moving until you encounter a null, right? So to identify your list, you need two things: a head and a stamp at the end that tells you you have just done, right? If you are looking for a certain value, you start from the head, you keep traversing, but when to stop, you don't know, right? If you don't make your next to tail null, then you cannot almost do anything with because you will keep in like an infinite loop, right? And you will access an unidentified memory, you will have segmentation fault, so it will not work, right? So the special thing about the tail node is its next is null, and it has to be null, right? Is that correct? Has to be null? In a single linked list, that's correct, but there is one data structure that is called circular linked list, where the tail points to the head. So you can create, with this very little change, you can make a single linked list, a circular linked list, by making the tail point to the head, right? You see, we move, once you have the fundamental of a certain data structure, you can do very slight changes to define a totally new data structure. It has its own properties and it has its own problems, advantages, etc., right? So from a single linked list, now we added the previous link. We had a doubly linked list, which is a completely in its own data structure. And you also, by this very simple change, by making the tail point to the head, you made a simply single linked list into a circular linked list, right? Very slight change. Yes? But generally for SLL, it's just a null at the end. Good. For a doubly linked list, we also have two special cases: your head and your tail. Your head now has a next, which is the normal one for a single linked list, but also it has the previous. What about the previous of the head? What should I set this? In a doubly linked list, what would be your previous for the head node? Null. You don't have something before the head, so it has to be a null, right? What about the tail? The tail, the next would still be a null, similar to the single linked list, and its previous will be the node that is before the tail, right? Good. You make the first node point to the last one. Point. Yeah, so that means now the first node, it has a next, which is the node after the head, and then it has another pointer that points to the tail, right? It has to be another pointer, otherwise you lose your next, right? So, and you do this. One problem with this may be valid, your own data structure. Why it's not common? For two reasons. The first one is now the first node is not the same as all the other nodes. Usually people tend to create data structures that are homogeneous or identical on their own entities. For example, an array, it's like the most homogeneous data structure. All elements are the same size and the same type. Single linked list, double linked list, or any other type, you have a node, which is your own class, but then all nodes are the same. Right? You instantiate them using the same class. Now, the head would be a special, another class of node, right? You see the point? Because the head specially will have two pointers or two references, while all other nodes have only a single one. Make sense? The first one will have to have two. One that is pointing to its next, and the one that is pointing to the tail, similar to what you should suggest. Now you have to have two, right? Make sense? You mean in a doubly linked list? Also, you will still define, I thought what you said is instead of having a doubly linked list, do this, right? But in a doubly linked list, or what you're saying is instead of having it as previous as null, then make it point to the tail. Oh, that's completely valid, but now you create also a circular linked list, right? So this is an existing data structure where in a doubly linked list, the first node, the head, its previous is actually the tail, and the next of the tail is not null, it's also the head. This is a circular doubly linked list. So it's an existing data structure that is known. So you can do this as well. Good? Okay. So why would have a new data structure? We discussed this by the deletion method. So let's see some advantages. Now you can traverse in both directions, and it can be essential for some programs. The very simple one is the delete, but this is a very basic one. Some operations, we said deletion, insertion for a node. Now the easier is an example of this. What are some of the disadvantages of doubly linked list? Without looking into the slides that you already have. What do you think? One important thing that you need, one important takeaway is there is no winner data structure. Real life is not like this. There is nothing that is the best and all others are dumb, right? It doesn't work like this in real life. Every data structure, even if it's very simple, including arrays, actually arrays are the mostly used data structures even in production software. Why? It's very simple. Because it has real use cases, right? Its access time is constant time. Any element you can access is contiguous in memory. So it has its own advantages, right? If you use cases like this, okay, use it. Simple, that's great. Simplicity is an advantage, not a disadvantage, right? So the main point is there is no one winner data structure. Good? Single linked list has some advantages over the doubly one. What are some of these advantages? Everything you can do in a single linked list, you can do also in a doubly linked list. Is that correct? For sure, right? So why some programs use a single linked list? Yeah. Less memory, correct? Why less memory? Yeah. Exactly. For each node, you define a new instance field, which is your previous, right? This takes a place in memory. It's a reference of a type node. So it can be like 32 bits, 64 bits, right? Based on the node size. So now you create for each node, you almost double the size of your linked list. This is one thing. What's the other thing? Can you think of another thing? When it comes to data structures and algorithms, yeah. Why? Your tail is still, its end is null, right? Yeah, I guess maybe what confused you is what I was answering his question where you have a circular doubly linked list, but generally you don't have this. It's like just a doubly linked list where your tail next is null, your head previous is null. So it still can do the same thing, yeah? Yeah, it's slower to create new nodes because now what you would do, or delete even nodes, and what you would do, you need to change two references, two links, not just one. So it's slower, right? Good. And also, it's harder to maintain. This is arguable because it's very similar to single linked list, but in general, any more complex data structure, that means more probability of errors and also harder to maintain, right? So keep it as simple as possible, especially when it comes to algorithms and data structures. Yeah. Yeah, one very easy example is assume you have a data that is, I don't know, like 1 gigabyte. You know that your data structure is 1 gigabyte, right? Allocating a 1 gigabyte array, which means it has to be a contiguous 1 gigabyte. Most of the times it doesn't work for normal machines. And the reason is you need a contiguous 1 gigabyte at a time. What about linked list? You will still use the 1 gigabyte, but then what is the disadvantage? What is the advantage of this? Why it will work even arrays don't work? They are distributed, right? If your if your memory is just one chunk like this, one list can be here, one node can be here, one node can be here, one node can be, right? So what we said before is this structure this structure may seem like one after the other, right? But in reality, in hardware, in memory, this is not the case. This node can have the address of 0. This can have the address of like FFFF. This can have the address of 3, 4, something, right? They can be anywhere in the memory. Why this is allowed? Because you keep the address of this in this node by this link. So another way to understand the link is it's just the address of your next node, right? This is just an address, right? A reference, like exactly as a pointer. A pointer is holding an address, right? A reference is also holds the address of the object that it points to, right? So if you have the address, it doesn't matter where the node is. Right? There are also many other use cases, but this is just like a simple one. Yeah. Would you say this again? Yeah. Yeah. Remember from C, we said the index of the array is an address but with some arithmetic operation. So AI, you hold the address of A, which is the beginning of the array. To go to I, you need to add I multiplied by the size of the array entry, right? Yep. Yeah, in C, because you can handle memory dynamically, we have seen ways of declaring an array without even saying its size, right? So you can also, if you already declared a certain size using malloc, you can later make it bigger or extend it, as you said, by using reallocation or making another malloc and then copy your data from the old one. So you can do this for sure. But this is time consuming, right? You have to create a new one, copy the old data, so it takes time. Okay, so now it's time to write some code. Previously, we had this node class, which we called LL node, where it only has the value and the next pointer, and then this is its constructor. And from there, we created our single linked list class. In this class, we also had 3 methods, right? Which is like insertion at the beginning, insertion after a node, and deletion, I guess. Or traverse, we didn't write the deletion one. So my question to you is how to modify this code to identify or to create or to define or to declare a doubly linked list. Will you take 2 minutes to modify these 2 classes? In fact, you need to modify both, right? It doesn't. Do we need to modify both? Yeah, so let's modify both to create a doubly linked list. It's a very slight change, right? Again, what you need to do is you have this, which we created last lecture for single linked list. This is the node class. This is the list class. We want to create a doubly linked list. What do we need to change in this code? Yeah, I give some time to write, and then I'll ask, right? Anyone done? Yeah. What do you do? Okay, good. And then create. Okay. Do we have to define this? You need to define the tail for the doubly linked. We can still also add the tail to the single linked list as well, right? And we didn't do. So is there any difference that I need the tail for? the doubly linked list. But you have the head, right? The head allows you to move. But usually you are correct. Like, because now you can move forward and backward, it's better. It's better, right? It's not necessary, but it's better to add the tail, right? Good. Do you see that? So what we change here is okay. Somewhere. Is it view only? Okay. So what do we do here is we add the previous one, which is LL node, I don't know, call it previous. Then here you might and might not have a variable that you call previous. Then you set previous to this. And then here, let's call this doubly linked list. Then has a head and it has a tail. Is there any question here? So this is also type of what you should expect in, for example, in exam or in fact in real life. It's rarely you start writing some code from scratch, right? You work on projects like you will be adding something, you will be modifying something. So in the exam, maybe I give you one class and then I want to create another data structure from some data structure you already know. It may seem hard because now you get introduced to a new data structure, but it's similar to what we have done in lab. As I said before, you would be able to do lab 5 completely without knowing anything about linked list. Why? Because it's just an abstraction or understanding of the concept. It doesn't really matter. At the end, everything is classes and references to classes, right? So what we created here, in other words, like this is just for the programming language, just a class, right? It doesn't understand this is a doubly linked list and doesn't even understand the structure of the linked list itself. This always like a kind of an illusion that we have in our mind, right? In reality, it's just a simple class. Good? Do you have any question? Okay, so now given we have our doubly linked list, let's first see this and then I'll ask you to write, right? So how to delete a node from a doubly linked list? Now it seems to be much easier, right? Because what you need to do is, what do you think to do? What are the steps that I need to do to delete a node from a doubly linked list? Yeah? For the node that you want to delete. But first you need to go to the node that you want to delete, right? Which is traversing, yeah. So the first step is to traverse to the node you want to delete. And then once you are there, what you are saying is make, yeah? Exactly, right? And now you don't need the headache of like 2 references or know what is next. Once you are in the node that you want to delete, you already have this link and this link. Make the previous one point to the next and then the next point to the before. So just modify this link to be this, modify this link to be this, and then you are done. A question is, I didn't do anything with this node. How does this delete this node? Like a repeated question from last lecture. Yeah? Yeah. Exactly. This is one of the biggest changes in Java compared to C. In C, if you create, by the way, you can create, this has nothing to do with C or Java, right? Did I say this before? Data structures are not related to any language. You can write them in any language. Again, it's just an abstraction, right? So if you create a doubly linked list in C, and then you do this deletion, in fact, you have to delete the node yourself, right? By either making it as null and free the memory that the node is pointing to. Good? In Java already does this for you because you don't have memory management, self-memory management in Java. You don't do this yourself. Good? So every period of time, like milliseconds or whatever, the garbage collector of Java, which is part of the Java virtual machine that we discussed in the first lecture, is going to look into all your objects, see if there is any object that has no reference to it, right? Remember, this node is still pointing to this and this, but these references are out of the node. It's not into the node, so it doesn't really matter. What the garbage collector is looking for any object that has no reference into it, and then it will delete it, because that means you are not using it anymore. Good? Okay. So, because we didn't write a delete method on Monday for a single linked list, so let's write a delete method for a single linked list and see what we change for the doubly linked list. So what I want you to try is to write a node, write a method that we call delete node. You get the value, assume that you have a list of integers, and then it returns a bool, and then you delete the node that has this value for a single linked list. Can you take like 3 minutes to write this? Like, again, this is for single linked list, not doubly linked list. We will write the doubly linked list afterwards, right? How to delete a node from a single linked list. Another hint for the exam that I said before is, and this is one example of this, we already discussed how to do the logic, right? We already know this step, which I'll come into later. But then now it's time to put your logic into code, which is also challenging if your hand is not trained to do so, right? So I guess while you are trying to write, you see now how to translate your logic into a code, and it's not as easy as it may seem, right? This is kind of like an example that I know you already did, things that are harder in the lab. We already discussed the code. So you should already know what's going on, right? Is there anyone done? Yeah? So how to do this? So great. Yeah, you don't, yeah. Yeah, thank you. That's a perfect code. So one small change I intentionally made in this slide compared to what we discussed at the beginning of the lecture is I asked you to return something, which means you are doing some additional checking, right? Previously we said you look for the node that you want to delete. In a single linked list, now you are one node before it, and then you make the next to the next, and then you are done. But there are multiple special cases. First, what if your linked list is empty? Doesn't have anything. Then you don't need even to traverse. And this checking is always done. If you look into any professionally written code for linked lists, this is the first checking, the first line of any method that is done, right? Why? Because you save your time. Your list is empty, you are done. You don't need to traverse anything, right? One thing. But by the way, this is already taken into account in your while checking condition, because you check if your next is null, right? Then you are done. But now you are yourself is done. Is null. So these are two different conditions. If you are null, you don't even have a next, right? You need to check if your head is null, then your list is empty, and then you return false. The other special case is, what if your value is not even in the list? I'm giving you a value. Previously, we assumed that this value is guaranteed to be in the list, right? But you may traverse the list from the head to the tail until you encounter a null, and you don't find the value. In this case, this is another special case. You don't do any deletion, but then also you return false. This is the reason why we have a bool as a returning type, because you return false if you didn't find basically if you didn't do the deletion, whether you have an empty list or you didn't find your value. Then, after these two special cases, the normal situation is you do the traversing until you hit your list, until you hit your node, but you are before it, and then you make the one before it point to the next one, right? Is there any question here? Is that good? Okay. So what if I want to write exactly the same method? Maybe I don't have another slide for this. For a doubly linked list. And you also take like 2 minutes to see what will happen if we do this for a doubly linked list. What would be the code that you would write? If you guys don't write, and then I guess if you don't have questions, that means you didn't try to write and encounter some cases, right? So make sure you try to exercise. This is the time you are already here in the lecture. The time is already wasted anyway, right? So let's utilize it to try to train yourself and have a time to interact with me to ask questions in your code, right? So take 2 minutes to try to write this method for a doubly linked list and see if you have any questions. Current.previous.next is yourself, right? .next to previous is yourself as well, right? It has to be current.previous.next equal current.next. Yes? Is anyone done? Is anyone done? So let's see what is happening, right? So first of all, I try to look into the special case that I just mentioned, which is you just have an empty list, so your head is already null, right? In this case, I don't delete anything, I just go back, right? And then now I set my current to be the head, because I'm starting from the beginning of the list, and keep moving until I reach, or until I encounter, oh, here I just didn't move the current, right? Big mistake. Right? Do you see anything else that is wrong in this code? Yeah. Exactly. This is one of the things that why we said you need to look into the special case if your value is currently in the head, right? Why? Because assume your value that you want to delete is just the head, right? What do I do? And I'll come into discussing this code like the main part, but let's look into first the special case. And this is how you think of any method or any action you take in a data structure. First, think before writing any code, think in all the special cases that you will encounter. Empty list, a list with only one node, and what would happen in this case. Put your code aside in this, and then the main part of your code would be the other part, right? Even if you are in a coding interview, you should do the same thing. You're actually looking into whether you identify the corner cases or not, right? So what Arun said here right now is, what if the value is in my head? In this case, I will still find it because initially my current is head, and the head is not null, so the condition is true. This condition will end up being true, which is current with value equal value. But then when I say current dot previous, and I'm at the head, my previous is null. Null.next is segmentation fault. Remember your midterm? You cannot reference something that is null in the memory. It does not even exist. So it will give you a segmentation fault here. That means it's a special case you have to handle away from this main part of the code. Where to handle it? At the beginning, right? Then you need to say, if, what do I need to say to handle this case? Yeah? Hit the previous is always null, right? What is the special case that I just mentioned right now? Yeah? Yeah, your value is in the head, right? So head with value equal value. In this case, what would I do? What do you need to change? Yeah? If you did this, you have just done exactly what we were trying to escape from. Because head dot previous, oh, you say head dot next dot previous. I see, okay. Yeah, sorry. Yeah. Is just to null. Yeah, exactly. Yeah, exactly. Or a simpler way is just make the head equal head dot next, and now you have no, but you still have the previous of this one, so you still need to set this to be okay. So we can say this head equal head dot next, and then now head dot previous just equal null, right? Yeah. I guess that's simpler than saying previous next. Yeah? Exactly, right? So now you have one special case, which is your value is in the first node, but now we assume that you have more than one node, right? So you see now where we go, right? So this takes us to, there are not always, right? But to be in the safe side, and this is a hint that maybe no one else tells you, is for data structures, especially linked lists, look into these special cases. You have an empty list. You have a list of only a single node, right? The case that Arun is pointing to is, what if I only have one node, which is the head? If I write this code, I would say, okay, head equal head.next, but because my head was just one node, that means .next is just a null, right? And then now you say null.previous. This is segmentation 4, right? So no nodes at all is special case. Another second special case you need to look for is you only have a single node, right? Think of, if you only have a single node and you are going to delete this node, that means you are making your list empty, right? Make sense? Yeah? So the third special case that I was mentioning is you find your other list at the tail, right? Okay. So what do I do in this case is I just say if head. Maybe I'll ask you how to handle this special case. If you want to delete a list, if you want to delete a node from a list, and it happens to be this node is the head, and you have only one node which is the head. Yeah? Yeah, so you just make it null, right? So this is how you handle it. The way he said I want to check it is if your head.next is null. There is another way to check this in a doubly linked list, or if you have a tail, which is, this is usually one reason why people have tail in